Hey everyone, let's take a look at Achieve section 2.6 number 9. This is the problem here. The limit as x approaches 0 of x squared divided by sine squared of 4x, and it might be, instead of 4x, you might have, some other multiple of x, but it should be very similar to this. If you plug in directly, of course, the top is 0 and 4x is 0, so that gives you sine of 0, which is 0. You get 0 over 0. This is indeterminate. Okay, so obviously, we're going to be using one of the two limits we have learned, right, from the lecture in section 2.6. And obviously, let me show you up here in this corner. This is the one we're essentially going to be using here, right? I proved this limit with a long geometric proof involving the squeeze theorem, but this limit can now be assumed. So on the test, actually, if you need this limit, it's on the trig help sheet. So we have that limit, okay? So the limit as theta goes to 0 of sine theta over theta equals 1. Keep in mind, it's very important to realize if I get rid of that limit sign, sine theta over theta equal 1 is false. Sine theta divided by theta is never equal to 1 for no value of theta, okay? The whole thing is that as theta gets closer and closer to 0, again, the form of this is approaching 0 over 0, but that ratio is getting closer and closer to 1, right? So the limit as theta goes to 0 of sine theta over theta is 1. Sine theta over theta is not 1. So you cannot simply say sine theta of theta is equal to 1. Sine theta over theta is a function that varies for different values of theta. And again, at no value of theta is it ever equal to 1, it turns out, but it's getting closer to 1, again, as theta goes to 0. Okay, well, enough of that. I mean, that's what we're going to assume. Now, two things from this. So from this first one in the middle here, I want to just look at in this particular problem, because you've got the sign down below and the x up above. Of course, I'm using the variable theta here. I could replace theta with an x and it would be the same thing. But I wanted to just look at what's the limit as theta goes to 0 of theta over sine theta. Okay, again, that's indeterminate 0 over 0. But I can rewrite theta divided by sine theta as 1 divided by the reciprocal of theta over sine theta, which is sine theta over theta. And now the limit of a quotient is the quotient of the limits. So what's the limit as theta goes to 0 of 1 of a constant? That's 1. What's the limit as theta goes to 0 of sine theta over theta? That's 1. That's up here. So this is going to 1. In other words, the limit as theta goes to 0 of the reciprocal theta over sine theta is also 1. I mean, that's a direct consequence of this. Okay, so that's going to be helpful here. And then I want to just review also, I did this one in lecture video, the limit as x approaches 0 of sine of ax over x, where a is some non-zero number. Okay, pick your favorite non-zero number and put it there. What is that limit? It's not the same because it's got a sine of ax. This a cannot come out. You can't factor this out, unfortunately, because it's inside the sine function, right? So the limit as x approaches 0, if I plug in x equals 0, I get a times 0, 0, sine of 0, 0. Still, I'm in indeterminate form, okay? Now, what I can do, though, is essentially, since I'm taking the sine of ax, this will be the theta. I need to get theta in all these locations. I need to get ax down here and here, okay? How do I get ax down here? Okay, well, the easiest way is multiply the denominator by a. I can't just multiply the denominator by a. I have to multiply the numerator by a as well, because I'm multiplying by a grand total of how much? This whole thing right here, right, is equal to 1, right? A divided by a. So I'm not changing the value thing. So this a times x gives me ax. This a I can pull outside the limit because it's a constant multiple, provided this limit here exists. Okay, so all I've done is multiply top and bottom by a. So we have the a out here and the a down here. So that's just 1. But now I'm halfway there. I've got ax in here. I've got ax here. I just need to make this an ax. So what I'm going to do is I'm going to let theta be ax. Okay, just a change of variables here. And I'll have you note that as x goes to 0, that's our limit, x is going to 0. What's happening to theta? Since theta is just a times x, theta is going to 0, right? So as x goes to 0, theta goes to 0. So this limit as x goes to 0 is the same as the limit as theta goes to 0 of what? Sine of AX over AX. But what's AX? Theta. So it's sine of theta over theta. What's the limit as theta goes to 0 of sine theta over theta? It's 1, right? We still have this A out here, so A times 1. So this limit is A. In fact, that's true for this form always, okay? All right, so these are just reminders. This is what we've already done. Now let's go back to this problem. So you can approach this problem using both of these results here, essentially. And they all stem from this important limit. So this time I've got a 4x, right? That was like my A is like the 4. So it's very similar to this. So like I did here where I let theta be AX, I'm just going to let theta right away be 4x. Okay, and there as x goes to 0, again, theta goes to 0. So the limit as x approaches 0 will become the limit as theta goes to 0. It's the same thing, right? As x goes to 0, theta goes to 0. But I'm also going to have to replace x squared in this case, all right? So if theta is 4 times x, I can divide both sides and get x as theta divided by 4. Then if I square both sides, x squared will be theta squared over 4 squared, which is 16. So I can now replace x squared with this. The 4x is just theta. Everything is now in terms of theta, right? So it's the limit as now theta goes to 0, as we said that relationship here. X squared up top becomes theta squared over 16. And then since theta is 4x, sine squared of theta. Okay, so now I've just got everything in terms of theta. I just need to clean it up a little bit. There's 1/16, right? Really, theta squared divided by 16 is 1/16 theta squared. Let me factor that 1/16 out. Very similar to what I did here with factoring that A out, okay? And factor out the 1/16 out. That leaves the theta squared on top. And on the bottom, I still have sine squared theta, okay? But what is sine squared theta? That's sine of theta times sine of theta, right? It's sine of theta quantity squared. So it's sine of theta times sine of theta. So I'm just going to rewrite this out as theta over sine theta times theta over sine theta, right? Theta times theta is theta squared. Sine theta times sine theta is sine squared theta. Why did I do that? Well, now I have a limit of the product of two things. And our basic limit laws say that that is the product of the individual limits. And these two limits, guess what? That's this one right here that we talked about. The limit as theta goes to 0 of theta over sine theta is 1. So both of these are 1. So 1/16 was out here, times 1 gives me 1/16, and there's the limit. So there's a little bit of finagling here that we had to do to get this to work. But that's the what we have to do in this case. Now, if you want to always use this relationship that the limit as x goes to 0 of sine ax over x is equal to a, that's fine. But again, you're looking for this limit. It's hidden somewhere in all of these limits where we get 0 over 0. It's either this limit or the one involving cosine, right? There's two limits there that we use. Okay, I hope this is helpful. If not, let me know.